Alright, this is section 6.1 part 2. Let's talk about exponential growth and decay and what their graphs look like. So exponential growth, that will be an increasing function like this one right here, whereas exponential decay, that will be a decreasing function like this right here. So some equations for exponential growth and exponential decay. Notice all of these inside here, our base is positive for each and every one of these, and they're raised to an exponent that contains x in it. Okay, so these are all exponential functions. Now, we'll learn this a little bit later, that if b is greater than 1, then it's going to be an increasing function. Now, keep in mind this right here for just a second. So this is greater than 1, this is greater than 1, so these are going to be increasing functions. If b is greater than 1. Now, if b is between 1 and 0, you're going to have exponential decay. So notice this is less than 1 but bigger than 0. Less than 1 but bigger than 0. Now, keep this in mind right here. Notice that is greater than 1, so you would think it's exponential growth. This is less than 1, so you would think it's exponential decay. But when you've got this negative right in front of x, what that negative does right in front of x, it shifts the function over the y-axis. Okay, now notice this is what 2 raised to x is supposed to look like. Now when we have a negative in front of that x, it flips it over that y-axis. So when we just had 2 raised to x, we had an increasing function. But when I added that negative in front of x, well, now I have a decreasing function. Likewise with 0.75 raised to x, this was supposed to be a decreasing function, and it is when it's 0.75 raised to x. But when I add that negative in front of x, well, hey, now it's an increasing function. So determine if the equation represents exponential growth, exponential decay, this should be exponential, or neither. Okay, so number 1, it's not negative and it's raised to x, so it is an exponential function. And then number 2, I'm going to look at this number right here, 0.27, and I notice that that is between 0 and 1, which means we're going to have a decreasing function, which means we have exponential decay for this function. Okay? So determine if the equation represents exponential growth, exponential decay, or neither. All right, now we have a positive function raised to an x, so it is an exponential function. I'm going to look at this number right here and say, well, hey, b is bigger than 1, so it should be an increasing function. But notice that negative right in front of x. So that's going to switch it over the y-axis. So instead of it being an increasing function, it's a decreasing function. So again, we have exponential decay. Okay? We have a number raised to an exponent that has x in it, so it is an exponential. I'm going to look at this number here. Hey, it's bigger than 1, should be increasing. There's no negative in front of my x, so hey, this is an exponential growth function. Okay, we have 12 raised to x squared. Now that's an exponent raised to another exponent. That's not an exponential function right there. So this would be neither. Determine if the equation represents an exponential growth, exponential decay, or neither. Well, I have a negative inside there. We know that b cannot be negative and it can't be 1. So this is not even an exponential function, so neither. Okay, an exponential function, f of x equals a times b raised to x, passes through the points -2, 6, and 2, 1. So we're going to try to figure out what is a and what is b. So I'm going to set up two equations here. So first one with the -2, 6, and then the other one with the 2, 1. And notice this is on my x value, this is my y value, this is my x value, this is my y value. Taking this right here, we know that f of x is the same thing as writing y. So from this point, I'm going to go ahead and plot in what I know for x and y. So 6 is equal to a times b raised to -2. And we'll do the same thing over here. F of x is a times b raised to x, which is really just y, ab raised to x. So that would be 1 is equal to a times b raised to 2. So for this one over here, I'm going to go ahead and solve for a. So we're going to divide both sides by b raised to -2. So that -2 is going to push it up. So that would be 6b squared. Okay. And then what I'm going to do is I'm going to substitute what I know for a into this formula over here. So 1 is equal to 6b squared times b squared. So that is b raised to the 4th. We're going to divide the 6 from both sides. Okay, so then from there, we've got b raised to 4 is equal to 1 over 6. Okay, so there's two ways I could do this. We could do this right here, take the 4th root of 1/6, or another way is to raise both sides to 1/4, and that might be easier on the calculator. Okay, so you would need to grab your calculator at this point and type in 1 over 6, get a number for that, and then raise that to 1 over 4. Sometimes you'll see something that looks like this. We call it a caret, or you see x raised to y. Both of those are talking about having exponents on your calculator, okay? So let me get my calculator out. So we have 1 divided by 6, get a number for that. And I'm going to raise it to 1 divided by 4, close out the parentheses. Looks like that is 0.6389. 0.68, let's see. Uh, 0.6389. 0.6389. Okay, and then, so that's approximate. Then I'm going to come back over here to A and plug in what I know for B and solve for this one. 0.6389 squared. Okay, and if you want to, you could do 1 divided by 6, just do this over again, raised to 1 divided by 4, get a number for that, raise that to 2, and then multiply it by 6. So we should get 2.4495. Now, that's using the entire thing. Let me show you what happens if we use just the 4 numbers that I have there. So it's, let's see what, 389. Okay. So 0.6389, square that number, and then multiply it times 6. Oops. 2.44915, so that would be 0.2. So since I have just the 0.6389, just have that squared, I'm going to have a 2 right there. So there's my A, and there's my B. Now let's look at something called the compound interest formula. Okay, so the formula that you would use when you're trying to find compound interest is this right here. So P is the compound interest is equal to P times 1 plus R over N, and then that raised to N times T. Okay, so they say that A of T is the account value. T is measured in years. P is the starting amount in the account, called the principal. R is the annual present rate. And N is the number of compounding periods in 1 year. How many times does it compound in a year? So look at this one. An initial investment of $700 earns interest for 14 years in an account that earns 11% interest, compounded semi-annually. Find the amount of money in the account at the end of the 14-year period, round to 2 decimal places. Okay, so P would be the 700. That's the starting amount. And then T would be 14 years. R would be the percent interest, so we got to get that out of percentage, so that would be just 0.11. And then N, how many times did it compound in 1 year? Well, semi-annually, that would just be 2. Okay, so what we have is we're trying to find after 14 years how many or how much money will be in that account. So we'll have 700, 1 plus, and that's going to be R, so 0.11 over here it says N is 2, and then raised to T times N. Okay, so we'll just take this a step at a time. 1 plus 0.11 over 2, and then 2 times 14, that's going to give you 28. Now let's look at 1 plus 0.11 over 2, see what we get there. So 0.11 divided by 2, and then plus 1, 1.055. Then I need to raise that number to 28. So 1.055 raised to 28. Okay, I get that number. And I'm going to go ahead and multiply times the 700. 31, 34, 49. 31, 34, 49. And there was a 0 after that. So it says round to 2 decimal places, so that will be my final answer right there. So that's how much money should be in that account when you invest $700 for 14 years at an interest rate of 11%, compounded semi-annually. It'll be this right here.